What we saw with the argand diagram is we can represent a point on the number plane as a complex number. But there's another way of labeling that point which can be very useful for some of the work that we have to do, and it's called Mod-Arg Form. Modulus. Actually, you know what modulus is. You might not realize it. But the modulus of a complex number is the length of the vector OZ. So there's my number, x plus iy. The length of that vector is the modulus. What do you already know that finds exactly the same thing? All right, absolute value. The only reason you didn't realise it is because, of course, all the numbers you've been dealing with now have just been on the number line. So it's just been a straight distance. But when you think about it, it is the distance from the origin. And that's all this is, the distance from the origin. So, in a way, okay, Pythagoras, yes. You could think of it like that. Because to work out the modulus, we would have to use Pythagoras' theorem. So x squared plus y squared, there's that real part plus imaginary part, so the ZZ conjugate. And there's the notation. And that's what I mean, you've seen it before. The notation actually is absolute value of Z, but it's actually modulus of Z. The argument is the angle that vector makes with the positive x-axis. And we've seen that before too somewhere. Where was that important? The angle with the positive x-axis. Yeah. Remember that was the other way of finding the slope of a line. We said slope was equal to tan theta. So it's the same sort of idea. So the argument would be that angle in there, which we've labelled with theta. That's what's called Mod-Arg form. In mathematics, it's also known as polar coordinates. However, because theta is an angle, and as you know, we can go around the circle 360 degrees or 2 pi and still be at exactly the same point. So I could give you the answer pi on 3. Someone else could say 7 pi on 3, and we're in exactly the same spot. Well, we don't want different answers. So there is a convention for argument that we only give our answers between plus or minus pi. So plus or minus 180 degrees if we talk about degrees. So plus or minus pi. Now, plus pi and minus pi is the same thing, because if you go around 180 degrees that way, 180, you're in the same spot. So that's why I haven't included minus pi. If we're over there, then it's pi we use, not minus pi. 4 minus 4i then. Let's find this modulus and argument. So 4 root 2 would be the distance to the origin. 4 root 2. So that's the modulus. The argument, now this is where we've got to be careful. It's minus 4 on 4, which is minus 1. But we have to be careful. So I like to draw a little diagram to see where it is. I'm in the 4th quadrant. So if I'm in the 4th quadrant, I want a negative acute angle. You see, tan of minus 1, it would also be true over here in the 2nd quadrant. So I need to know where exactly am I. Am I in the 4th quadrant? Am I in the 2nd quadrant? So I know what sort of angle I want. Inverse tan of 1 is pi on 4, so minus pi on 4 is the argument. So every complex number then can be written uniquely in terms of its modulus and its argument. So z equals x plus iy, that's in its traditional form, or I suppose you could say its Cartesian form, is equal to r cos theta plus ir sine theta. Why is it that? Well, if you go back to that triangle and have a look at the x side, you could say x over the radius is the cosine of theta. And y over the radius is the sine of theta. So that allows us to convert from the Cartesian coordinates to the polar coordinates. And it factorizes out. There is a shorthand way of doing it. So the correct way of writing it is r outside of cos theta plus I sine theta. The shorthand way is just writing cis theta. And the reason people do it is because cos theta plus I sine theta, theta's always going to be the same anyway. So rather than writing cos plus I sine, we sort of abbreviate it into this cis. So r cis theta, but it means cos theta plus I sine theta. So r is the modulus, theta is the argument. So 4 minus 4i is the same as 4 root 2 cis minus pi on 4. Root 3 plus I then. Well, its modulus would turn out to be 2 when we work out its distance to the origin. And its arguments, inverse tan of 1 on root 3, that's in the first quadrant because they're both positive. So it'll be pi on 6, pi on 6. So 2 cis pi on 6. What about if we're going the other way? Convert 6 cis pi on 6, and we've got to get it back to that Cartesian idea. Well, that's where it's important we remember what cis stands for. Remember, cis stands for cos plus I sine. And so I can go and work out what is the cos of pi on 6, what is the sine of pi on 6, and then multiply out by the 6, and we get my answer, 3 root 3 plus 3i. Right, so some relationships that allow us to play around with these. The modulus. What this is saying is it doesn't matter which order you do it in. You could multiply two complex numbers together, then find its modulus. Or you could find the modulus of each individual number and multiply that together. So the order that you do that in doesn't matter. Argument though, we don't multiply the arguments together. We add them. Similar to something else we've seen. Anyone remember where we've seen that idea before? With multiplying, we actually add. There's another function we do that with. What was it? Logs, yeah. So it's the same idea. But remember we talked about yesterday, the rotation. I, if you think where I sits, the argument of I is pi on 2. So this is why it was a rotation of 90 degrees. Because what you're actually doing, when you're multiplying it by another complex number, you're adding the angles together. So when you multiplied by I, you added 90 degrees to the angle. And that's true for any size angle, and that's what this is saying. If I wanted to look at the picture and I work out where it is, I get the two angles, add them together, and that's where the new complex number would be. Quick little proof here. Z1 is R1 cis theta 1, Z2 is R cis theta 2. So if I multiply them together using good old algebra, whoa. But look at what we've got. Cos minus sine. And for the imaginary part, I've got sine cos sine. They're familiar. Well, cos, sine. If it's not the sine, it's not the sine. Cos theta 1 plus theta 2. Sine cos sine. If it's the sine, it's the sine. Sine theta 1 plus theta 2. And so there's our proof. The argument becomes adding them together, whereas the modulus is when we multiply them together. Now, it logically follows that if I have more than one number, I would just keep doing that pattern. So if I had to find the modulus of Z1 times Z2 times Z3 times Z4 times Z5 times Z6 up to Zn, I could find all the individual moduli and multiply them together. Whereas with the arguments, I would add all the different angles together. Right, division, very similar. Again, does not matter which order you do it in. And for the argument, we would subtract the angle that we're dividing by. And someone asked that yesterday, remember. They said, oh, well, hang on, if we were dividing by I, would we rotate clockwise instead of anti-clockwise? And that's what this is saying. We would subtract the angle, so we would go the other way. And again, a logical pattern. If I had something like this, modulus of Z1, Z2 over Z3, Z4, I could find the moduli of each individual bit and then find the answer. With the arguments for this one, the ones that are on the top, I'd go plus. The ones that are on the bottom of the fraction, I would subtract. This one then becomes really interesting. If I want to raise a complex number to the power of n, then z to the power of n, I could just find the modulus of z and raise that to the power of n. Because mod z to the power of n is mod z times z times z times z times z times z times z, and so on. So I could do that by going mod z times mod z times mod z times mod z times mod z times, So I'd have mod z to the power of n. Whereas with the arguments, again, like logs, I could bring that n to the front and say the argument of z to the power of n would be n times the argument of z. All right, let's work this one out then. The long way of doing it, I could actually go and calculate this out. And I'd come up with a number and then I'd have to work out the modulus and argument of that. I think using these rules, it's quicker, because to find the modulus of this, I'll find the modulus of each individual bit. And that's going to be a lot quicker. So the first one's root 5 squared plus 1 squared. Second one, minus 2 squared plus minus 1 squared. And on the bottom, we've got 3 squared and 2 squared. Root 3, oh wow, didn't those numbers work out nice? Look at that. Root 13 goes into root 26. How lucky am I? Root 10 becomes the modulus of that particular one. So I didn't actually have to work out the new complex number. The argument, then it would be the inverse tan of 1/5 plus the inverse tan of minus 1 on minus 2. So I'm over in the fourth quadrant. No, third quadrant, isn't it? They're both negative. Yeah. Minus the inverse tan of 2/3. Couldn't do radians for this one. I thought I'd go to degrees. I could have used radians, but I still wouldn't have known exactly. But I've gone degrees and minutes on this one. So minus 175 degrees 48. If I now wanted to work out the answer, I could say, well, it's r cis theta, and I could work out the cos of minus 175 plus the sine. It'd be an approximation, but you know, hopefully it'd be a pretty good one. I'd probably just leave it in the polar form. Okay. Wow, that seems like a lot, doesn't it? Mind you, remember what I said.